I've had a request to do some exam-style moments questions, so here we go. I'm going to start fairly easy and work our way through a little bit more difficult before we go back to more straightforward ones again. We have a uniform rigid rod AB, and let's zoom in on AB so we can see what it is. Anytime you meet a moments question, the first thing you do is identify the pivot, and then you look at the forces that would tend to move the object around that pivot. So this one is straightforward because they've identified the pivot for us. The force at A, that's going to cause a moment around the pivot in that direction. And of course, the only balancing force is on the other side, it's the weight, and so that's going to tend to tip that side in a clockwise direction. And if we want the rod in equilibrium, we have to balance those moments out. We know that this weight here is 6.5 newtons, and we just need to know the distances of both of those forces from the pivot. Now it tells us it's a uniform rod, so that means that that weight is going to act from the center of gravity, which is going to be the center of the rod. And since we know that the rod is 1.5 meters in length, then we know that this W happens at 0.75 meters along the rod. So we need to take all that we know and put it together. The distance that we don't know is this one, and we'll call that x. Now, we don't know this distance in here either, but we know that that distance is going to be 0.75 meters minus x. So we can say that y is 0.75 meters times x, and y is the distance that the weight is from the pivot. And then the other side, the distance of the 3.5 newtons from the pivot, will just be x. And we're going to solve it for x. So we know that the moment is force times distance. And that is our perpendicular distance from the pivot. And if we have equilibrium, then we need to have the moments on the left, the anti-clockwise moments, equal to the moments on the right, the clockwise moments. So we're going to say 3.5 times this distance x, because that's the distance that force is from the pivot, is going to be equal to 6.5 times the weight's distance from the pivot. And we've called that y, but we know that y is 0.75 minus x. So we're just going to substitute that in there. Now all we have to do is solve this for x. I'll do it the long way so you can see me doing it. 3.5x is equal to, and we're going to multiply out this bracket, 4.875, that's 6.5 times 0.75, minus 6.5x. We're now going to take this and bring it across, and of course it becomes plus once you bring it across, and 6.5 plus 6, and 6.5 plus 3.5 gives us 10x is equal to 4.875, leaving us an x of 0.48, and let's round up the last two, 8 meters. Our next one is a 5-mark question. Lots of information that needs to be picked out of it, but once you do that, it's pretty straightforward. So we've got a diver of 680 newtons sitting or standing on the end of a diving board. It has a length of 3.6 meters, so the total distance across here is 3.6 meters, and is fixed at the end labeled x, supported at position y, which is 0.9 meters from x. Diving board is uniform, so this tells us then that the weight of the diving board will occur halfway along the length. So we know that this force here is happening at 1.8 meters from x and has a weight of 390 newtons. So we've got that information there as well. By taking moments about x, that tells you x is our pivot. So we're measuring everything from there. What is the upward force exerted by y? Now, diagrams like this can get very messy once you start adding the information in. So for yourself, it might be a good idea to sort the diagram out, make it more meaningful for you, so that the forces and distances are all clearly labeled. So let's do that first. There's our position x. We have the force we're trying to find at y. we have the weight of the diving board there, which we know is 390 newtons. And we have the weight of our diver, which is 680 newtons. We can see that the diving board weight and the diver weight are all going to cause a clockwise moment about x. So those are going to turn that around in this direction. The force from our support is going to do the opposite. It's going to provide an anti-clockwise moment. So if the diving board is in equilibrium, the sum of the moments that go clockwise is going to be equal to the sum of the moments anti-clockwise. Now, to find those moments, we need distances. We know that f is 0.9 meters. And we know that the diver is right out at the end of the board, which is 3.6 meters out. We also know that our weight is halfway along, which is 1.8 meters out. So now we have all the distances and the forces that we need in order to balance these moments. So we're going to go force times 0.9, that's our anti-clockwise, is equal to 390 times 1.8 plus 680 times 3.6, giving us the sum of the clockwise moments. And again, I'm going to do this out as a full calculation. That's 702 plus 2448. 0.9f is 3150, giving us an F of 3,500 newtons. The next question is the sort of one that frightens students because it looks horrible, and there's a lot of blurb up here at the top that you don't actually need, but of course you have to read because in case there's any information in it and you might miss it. But essentially we're going to the force diagram at the bottom, which again is accompanied by quite a bit of information, and so we're going to examine that a little bit more closely. First point to note is that constant thickness, so we know that it's uniform, which means that the center of gravity of this beam will be halfway along. Then we have its mass. And the first thing we can do is turn that mass into a force by multiplying that by 9.81. And so we'll do that straight away. That gives us a force of 2.99 times 10 to the 5 newtons. Then it tells us the length of the beam is 11 meters, so we know that that weight will be acting 5.5 meters from the end of the beam. And we're going to redraw this beam to make it much more simple in a moment. In its resting position, so by this it means equilibrium, which means our moments will be equal. The steam cylinder rod is supported by the base of the steam cylinder. All of this is supported at an angle of 20 degrees to the horizontal, so as we see in the picture. And we want to find out the force T. So let's have a little redraw of this diagram so that it makes it clearer for us. We have our T acting on that end. We have our pivot P, and we know that along this line, that is 6 meters. We also have our weight acting down this way, and we have a value for that weight already. And we know that weight is 5.5 meters from the end, which means from the pivot, it is 0.5 meters. So now we have two forces and two distances from the pivot. The only problem is that these forces are not acting perpendicular to those distances. So what we have to do is either find the component of the force that is perpendicular to that distance, or, which is probably easier in this situation, find the component of that 6 meters and that 0.5 meters that is perpendicular to the pivot. We know this angle is 20 degrees. So what we're going to say is that the moment from T is balanced by the moment from W. And we know that the moment is force times distance. So T times T's perpendicular distance from that pivot is going to be equal to W times W's perpendicular distance from that pivot. T's perpendicular distance from that pivot is drawn now with that pink line. So we can see the hypotenuse of that triangle, a pink triangle. Now the hypotenuse of that is 6 meters. 20 degrees is that angle, and we should be able to see that this side with the pink line on it is the cos of that. And so we're going to say T times 6 cos theta is equal to W. Now we have a value from of W that we calculated above. That was 2.99 times 10 to the 5. Let's put our weights triangle in blue. There's our perpendicular distance from the pivot to the weight. And again, it's going to be at an angle of 20 degrees, and it's the adjacent side to that. So it's going to be this distance here, cos 20. That distance there we know is 0.5 meters. So we have 0.5 cos 20. So now we have everything but t, so it's just a matter of doing the calculations. 5.64 t is equal to, if you multiply all of that out, you get 140,484, giving us a t of 24,908 newtons. Our next question is a little bit of forces on a slope combined with a little bit of moments. So we have a hiker here. These tend to be students' least favorite questions because they always get the triangles they should use confused with this. We have a hiker of 740 newtons. He's carrying a bag that has a weight of W. And they want us to come up with an expression for the normal contact forces R, given here, acting on the hiker's feet. The hill is at an incline of 20 degrees to the vertical. Why is this expression correct? Now, the best thing to do, again, like in many of these questions, is take the context away. Don't be confused by the fact that it's a hiker or anything else. So redraw the question to suit yourself. There's our 20 degrees. We have the weight of the bag acting downwards and 740 newtons, which is the weight of the hiker. Our normal contact forces, which I'm just going to label R1 and R2, are acting in that direction because they're perpendicular to the surface. Those are balancing the component of the weight that is also perpendicular to the surface. So they're going to be the same value as the component of the weight that is perpendicular to that surface. The rest of the weight, the component that is acting this way, parallel to the surface, would cause the hiker to slip down the slope if there wasn't friction involved. We're interested in the blue arrows here, the component of the weight perpendicular to the surface, and we can label that angle in there as being 20 degrees as well. Now we should see that those blue arrows are the adjacent side to those 20-degree angles. So we're going with cos. And the W, the weights here, W for the bag and 740 newtons for the person, that'll be the hypotenuse of those triangles. So we know that cos theta is adjacent over hypotenuse. So we know that our adjacent side, which is the side we're after, and which is the same size as R, is going to be W cos 20. Likewise, R2 is going to be equal to its blue arrow, which in this case is 740 times cos 20. Now the total reaction force or normal contact force here would be R1 plus R2, which would be W cos 20 plus 740 cos 20. But they've told us that the reaction force is the same on each foot, so R1 and R2 are the same. So we can say and if we rearrange that, we get W cos 20 plus 740 cos 20 minus 2R is equal to 0. And if we look back at the question, we will see that's exactly what they wanted us to show. The second part of this question is where the moments come in. And it says the diagram shows the lines of action of the forces acting on the hiker and backpack. Position O represents the middle of the back foot of the hiker, and we're going to take moments about O, and they want us to determine W. So let's zoom in on this picture a little so that we can identify what's happening where. This is our pivot, so everything we do is going to be taken from there. And we can see we already have distances to all of our forces from that along this line. And because in the last part of the question we have already resolved these forces into their perpendicular sides, we're going to use that information for the moments because we need the component of W that is perpendicular to the distance from the pivot, and we need the component of the weight here that is also perpendicular to the distance from the pivot. Now we've got three forces. We've got W, which is the weight of the bag, we've got the weight of the person, and we've got their front foot, this normal contact force R. We need to establish in which direction, clockwise or anti-clockwise, are these forces going to act around this pivot here. So we can see, I hope, that the weight of the bag is going to tend this direction around the pivot, and the weight of the person is going to tend that direction around the pivot. So when we do our moments calculation, those are going to be on opposite sides of the equal sign. What about our force R? Well, if you imagine sticking a pin in the pivot, the R is going to tend to rotate this line anti-clockwise in the same direction as W, the weight of the bag. So we're going to end up then with the moment of W and the moment of R added together are going to be equal to the moment of the weight of the person. We've already established that this is W cos 20 and this is 740 cos 20. So we don't need to do that again. And of course R is already perpendicular to that distance from the pivot, and they've given us all of those distances, so we can just go ahead and use those. It's important when you do these questions to be organized about your information. So you set it all down in front of you, just double check that you've got everything. So what we've got here then is W cos 20. That is our force that is perpendicular to the pivot, multiplied by 0.1 meters. So that's the moment of the weight of the bag. We have to add the moment of R to that, and that's going to be R times its distance from the pivot, 0.4. And then that's going to balance out with our 740 cos 20 times its distance from the pivot, which is 0.25. Now, you should already see a snag, because of course we have two unknowns in this equation. But this was the purpose of the first part of the question. We know that 2 times R is equal to 740 cos 20 plus W cos 20. So we can say that R is equal to that divided by 2 or multiplied by 1/2. Now we'll put that in, stick a pin in that for a moment and put it in later on, because let's clean this up a little bit, get rid of the causes before we start substituting in that. And also go ahead and calculate what that is so that it becomes easier to insert. Cos 20 times 0.1 is 0.094 times W plus. Now we're going to put in, for our R, 740 cos 20 plus W cos 20 multiplied by 1/2. We're then going to solve what the 740 cos 20 is, multiply it by 1/2, and when we do that, we get, and I'm going to leave the 0.4 for now, 347.69, plus find out what cos 20 is, and then multiply that by 1/2, and we get 0.47W. Okay, that's our R cleaned up. Is equal to, cleaning all of this up, multiplying all of that out, 173.69 0.84. We've still got cleaning up to do. We want to sort out what this is. So we've got 0.094W plus 0.188W plus, when you multiply the 0.4 by this, you get 139.076 will be equal to 173.84. Tidy this up again, bring that over and subtract it from the 173. 0.282W is equal to 34.764, giving us a W of 123.3 newtons. Now you might think that that's very laborious, you don't need to write all of this out, but it is very easy to get lost inside of this if you haven't made it very clear, and also you want your examiner to be able to follow your logic. So it is worth taking the time both for yourself and for the person who has to mark your work to put out at least a couple of the stages that you're going through so that they know that you're substituting correctly. And they're not just looking at the final answer to give you all marks or none. There's a sample of Moments questions. We've gone through pretty much the trickiest ones and the different kind of ones that can come up. I hope that's been helpful to you. If you have any other requests for questions that you'd like to see me do and talk my way through, then please do leave a comment and I will do them as soon as possible.